From Sacramento State, this is Beyond J, taking conversations from campus to the world. I'm your host, Philip Allstott. Is there a way to slow the spread of deadly viruses, including those that could potentially trigger pandemics? That's a question Sacramento State chemistry professor Kathie McReynolds has spent years trying to answer. Her research looks at therapeutic agents that are capable of blocking the transmission of infections from viruses such as HIV and coronavirus. The hope is that these substances could eventually be developed into drugs that can curb the spread of these diseases and potentially be used against future pathogens capable of causing pandemics. In today's episode, we talk with Dr. McReynolds about her groundbreaking research, the implications it could have for public health, and how she prioritizes involving students in this critical work. Dr. McReynolds, welcome to the show.
Thank you so much for having me.
Tell us about your journey to where you are now.
I did go to a sister CSU campus. I'm a Cal Poly grad.
Okay. Excellent.
I knew a little bit about a lot of different things, but I didn't know a lot about anything. And so that's what really pushed me into going to graduate school. Mm-hmm. I think I came out of my PhD understanding that there is a limit on what one person can learn.
Yeah.
But what it did tell me through that process of graduate school was that I was interested in keeping research going in whatever my career path was going to be, but I was also very interested in teaching, which was, again, a bit of a surprise. They graduate students all have to teach a certain amount, mostly to pay the bills. But at the end of that, I found that I really enjoyed working with students because I felt like I had so much in common with a lot of them. And so when I came back to California and was at UC Davis, I had only been in my postdoctoral research position for maybe about a year when I saw the job opportunity open up here at the Department of Chemistry, and I had never even set foot on campus, didn't know where it was in Sacramento, despite having lived in Sacramento for a year, and despite having also been from Northern California originally. So I interviewed for the job, and it was my first job interview, and lo and behold, they offered me the position. And 24 years later, here we are.
Wow, so this has really been your only
This has been
job.
my
this
only
has been
job.
Your career.
This is my career, yeah.
Wow, that's fascinating. And it sounds like what you're saying is that this, this epiphany that you had about the limitations, right, on what a person can do with their life helped you really focus in on what you want to do with that time?
Correct.
And at what part in your journey did you decide that this type of research was going to be something that you would dedicate your life to?
I think that came as a combination of both the work that I did as a graduate student, and I was at University of Arizona working with a really talented carbohydrate chemist, and she and I published a lot of papers together. We still collaborate even today. She's just now over at UC Davis. So when I went to my postdoc position, instead of looking at developing antiviral agents, what I was doing was still focused on looking at sugars, but now looking at them in terms of how cancer metastasis can occur. So, and it was a very different kind of project in terms of the types of techniques that I used. And what I found was I really missed making molecules and making molecules that had purpose. It was another sort of epiphany that just sort of directed what I wanted to do research-wise when I did get my own lab finally.
Mm-hmm. So if you could give us like the elevator pitch of what you're trying to accomplish, what would that be?
So what we are trying to accomplish is to develop something that does not exist, which is known as a broad-spectrum antiviral drug. Mm-hmm. You're probably familiar with broad-spectrum antibiotics. Mm-hmm. Yeah. That fights bacteria. Because viruses are so dramatically different from one another, and in terms of how they infect, the mode of transmission, all of that other stuff, there's no class of compounds that can be used currently to treat multiple types of viruses. And so that's what we're really trying to do, is have something so that the next time a pandemic rolls around, or the possibility of a pandemic rolls around, that there's something that you can potentially pull off the shelf and see if you can stop or slow down that transmission rate, and hopefully keep people out of the ICUs and emergency rooms and keep the hospitals going and functional.
I remember from a conversation that we had before that you were explaining the carbohydrates, the sugars, that, I don't know, it creates some strength that wasn't there before. I want to hear you talk about it.
Okay, so how our molecules are unique and interesting is that they are part carbohydrate or sugar based, and that's on the outside surface. They're kind of spherical when you get down to it. So the outside is a sugar-coated surface, but on the inside is a polymer. So polymers, plastic, anything that you come into contact with that isn't a metal or dirt or whatever is most likely a polymer. And so I didn't know anything about polymer chemistry when I came here. And so I decided to teach myself polymer chemistry and subsequently teach students how to do it so that we could build scaffolds. So the polymer is really a scaffold on which we then put the sugars, and the sugars are what I would call the active ingredient. And the sugars then have the ability to interact with the parts on the virus that are responsible for the first points of contact with our cells and cause infection. There's positive interactions between our molecules and the proteins on the surface of the virus that then they have an affinity to one another. So it's opposites attract. And so if they have that affinity, the virus is more drawn to our molecules than they are to the surface of our cells. Then what we can do is potentially block the interaction between the virus and our cells, which could then prevent infection from happening. And so these molecules, again, are spherical, so they look like a ball, right?
Yeah.
They're a sphere. And they have multiple points of contact that they can have with the structures on the surface of the virus, which also have multiple copies. And so what they call that is the multivalent effect, and I think that's what you were getting at. And the multivalent effect basically says if you have 1 + 1, that equals 2. But if you have 5 + 5, so 5 sugars interacting with 5 parts of the protein, or 5 different proteins, depending, the effect is not linear. So the strength of that interaction is correspondingly much higher than it would be if it was just one protein interacting with one sugar on either side. And so one of the people that I work with at Duke University, one of my collaborators there, said, we tested your molecules against these 4 different strains of HIV, and then we have this other virus that we throw in as a negative control, meaning our molecules, if they're specific for HIV, would give a negative result with this other virus, and they found a positive result. And I said, well, that's perfect. That's exactly what I want. And they were a little confused by that because I'm looking at something that's a non-specific kind of an interaction. And that non-specificity is what makes it possible to cover all these different types of viruses. We're still going to need vaccines. This isn't going to solve everything. But hopefully what this would do is buy us some time and keep people from getting critically ill.
Yes.
And so that's what we really lack. And that's why viruses are much more likely to cause pandemics than bacteria.
But what is the likelihood that you can develop something like this? So using current technology.
Yeah. So again, what I really have been focused on is what do these pathogens share in terms of their life cycle, their infection process. And so many antiviral drugs target one specific part of one virus, but rarely do they ever extend beyond one virus or one type of virus. So there's all these different families of viruses. And so when COVID popped up, and I figured out that there was some commonalities between HIV, something I was very familiar with, and this new virus that I didn't know a whole lot about, once I found that, I said, okay, we can already use the information and the knowledge that we've gained in studying HIV and apply it now to a completely different virus, different mode of transmission. HIV is predominantly sexually transmitted, whereas COVID is respiratory. And so what I decided to do was not focus so much on how they're different, but how they're the same.
Yeah. What would you call the thing that you're trying to produce?
I would call it a topical broad-spectrum antiviral drug.
Okay.
That's what I would call it.
And how far is the research away from providing something like this?
That is a really difficult question to answer. I would say that we have some really good data where we have found cross-reactivity between now 3 different viruses.
Oh, wow.
But whether or not these items could be formulated successfully, where they would be non-toxic and wouldn't create other problems, that's a whole nother level of study that needs to be done. So what I would say is the level that we're at right now is what I would consider preclinical. And there would have to be a whole lot of work that goes into figuring out how you would actually make a nasal spray or a throat spray, right?
Yeah.
How would you formulate that and make it so that it doesn't hurt the tissue that you're trying to protect, but instead serve as what I would call a molecular Band-Aid, so that it covers up the spots on our cells that the virus is looking for and makes it so that the virus can't find them.
And is there a challenge in making something that is like shelf stable that you could deliver and it would last in time to get to the person that needed it?
There would absolutely be that, and that is one of the parts of the studies that we're working on, is how to develop things that are stable at room temperature, something that could be in solution. It's not going to fall apart. You don't have to keep it in a refrigerator. Or if you remember when the vaccines first came out, there was a limitation because some of the vaccines had to be stored at an incredibly cold temperature, and many places didn't have a minus 80 degrees Celsius freezer to store those vaccines. So it has to be something that's practical.
Yeah, exactly. I don't want to dwell too much on, how difficult it is or how it's not working, because that's really exciting that you've seen something work across multiple viruses. You said you had something that attacked 3 different
viruses. Yeah.
Yeah, that's really amazing. And so I'm curious about how your research works. First, I want to ask about collaborators, because you mentioned that you had this one collaborator. This is a long time. How many scholars, researchers do you work with?
On a day-to-day basis, 1 or 2 at a time, but overall, over the course of this work, I've worked with probably approaching 10 outside collaborators. Some of them are within the Cal State system. Some of them I've never met in person. So it's a little weird how collaboration works, I would say, because you have these long-standing relationships with someone that you've never sat down in a room together with.
Yeah, well, that's
just how science works.
Yeah.
Sometimes by accident. Sometimes you ask around and say, "Hey, I need somebody that can do X, Y, or Z."
Oh, okay.
And do you know of anybody? But honestly, a lot of it comes out of me going to conferences and going to talks where I see somebody doing something that could be could correspond or be parallel to what I'm doing, or also be something that could help me. And then we kind of go from there. Sometimes you get a no, I'm too busy. If you're reaching out to them by email, sometimes you just don't get anything back. But a lot of times people are really, really happy to share what they do and share the tools that they have either discovered or instruments that they have in their possession that not everybody has. And so that's the way science works. And it's kind of a beautiful thing, to have these people that you work with, but you've never sat down and, had a beer with them or something.
Well, collaboration is something like coming from an art background. Sometimes you have to learn the hard way. Because, the ego's involved and you want to do this thing that you have complete creative control over. But I think even as an artist in that situation, you stumble across collaboration and you realize that now you can make something so much bigger.
Correct.
Right? It's got this new reach that you didn't have before. But it sounds like that is something that just already plays a role in the type of research that you're doing. Now, what about collaboration with students? Is this something that you're doing outside of the classroom, in the classroom?
So in the classroom, the types of classes that I teach don't necessarily overlap very well with my research. That's sort of one thing that is a little bit of a mismatch with me here. I was hired as a biochemist, and there is rationale behind that decision, but in terms of how I identify as an organic chemist or as a bioorganic chemist. And so biochemists, I would say most of them work on biological tissues or studying proteins or some sort of biological molecule, whereas I would say 95% of what goes on in my lab is what I would call synthetic organic chemistry, where we sit down, we map out what we want to make, we figure out how many steps and how many different chemicals it's going to take to get there, and then we actually go make those things. So it's very powerful to sit down and pull something out of your brain and say, this could have potential as X, Y, or Z, and then go into the lab and make something that has never existed before, nobody's ever thought of before. So there's a lot of creativity that goes into chemistry, which not a lot of people, I think, really consider. Most people think of scientists sitting in a room by themselves, but as you said, science is collaborative. We have to get together because there are certain things that I know how to do and I know how to do very well, and there's certain things that I don't know how to do and I don't have the time or the bandwidth to learn how to do. And so that's why collaboration is really crucial for science.
Yeah.
But yes, I do collaborate with students widely.
Well, it sounds like there's some difficulty in collaborating with students for you because of the mismatch between the classes that you teach and the research that you want to involve them with.
Yes.
So I guess I'm curious about why then you push for that. You know what I mean? There's obviously some flow that you're working against to get some students into the lab to collaborate with you, yet you are pushing anyway.
Well, there's nothing I can do about how I was hired.
Yeah.
I still think it's funny when they call me a biochemist because like I said, I don't identify as a biochemist, but yet that's been a majority of the classes that I've taught in my time here at Sac State. So what I rely on in terms of recruiting students is actually I rely heavily on my existing students. They do a lot of the recruiting for me. So the way that my lab is set up is I have graduate students, so at the master's level, and they then have 1, 2, or sometimes even 3 undergraduate students working with them. So my lab can get very large. I've had up to 16 students in my lab, and that's a lot for any one person to manage.
Yeah.
And so what I do is I break them into project groups, and those project groups are led by the master's candidate. And so the master's candidate knows what they want those students to do, so they show them how to do it. And then I oversee the projects, and I still get in the lab. I still have my own project. So when I don't have a broken arm, I do get into the lab.
I guess the thing that imprints on me is that you've made a major commitment to the research that you do, to the students that come into your lab, to just the ideas that are generated, and you're going to the conventions to bring more people into the fold and to develop the idea further. Where is that commitment coming from? Why is this important to you, and why do you continue to work on it when potentially this is something that's going to go on beyond the years that you have to put into the research?
Yeah, it's a really good question, and I would say, first and foremost, 100%, I love research. Research is so much fun. Mm-hmm. It's a way for me to just get in there and just go, what am I going to do today? Well, what do I want to do today? So there's so much freedom in having the ability to go in and say, I want to study this, and then go out and apply for the funding to do so. You get the funding, then you can actually have, money to make it happen, because chemistry is not cheap. Mm-hmm. And then you bring in a group of talented students. They don't initially know anything, and it's really, really cool to watch their development over time and watch their growth, both as a person, as a student, and as a researcher. The way that they think about things changes completely, and their ability to do well in their classes improves. So we call this high-impact practice, right? Research is a high-impact practice. I consider it to be one of the most important parts of my role as a professor and a teacher, because I can take these students into the lab and show them, a few techniques to start, and then they build on that, they grow, they learn, and then they start to have their own questions. Whoa, hey, maybe I should do it this way. What do you think? And I'm like, well, try it and see what happens. There's a lot of fun in that, and it's really, quite a process. The critical thinking development and problem-solving skills, all of those things can be applied to any area of life, any career. I've sent students, once they've graduated, I've got some MDs, I've got some other PhDs, I've got people that went on to PharmDs. They're all over the place. They're all over the world. It's really exciting to watch where they go.
Yeah.
And a lot of times they come in with the idea that they want to do one thing, and research changes that for them. Yeah. And that's one of the things that it did for me. It changed me. And so, again, I think it is one of the most important parts of my job, because what I'm really doing is training these people for what comes next.
Yeah. What you're doing has such potential to impact the world. I'm sure that there's labs, other campuses that would love to, poach you and have you perform that research, somewhere else. Like, what is it about Sac State that has kept you here for so long?
I think Sac State, to me, the students here all remind me of myself at their age. This young person that's got a lot of ideas, but not really any direction. Yeah. And just kind of got sent to college as, well, go figure it out. Yeah. I grew up in a single-parent household with my mom, who was a teen parent and didn't have the opportunity to go to college. And without the help of the faculty that mentored me as a young student, I wouldn't be here.
Yeah, honestly, it sounds like that's the only way to get these big things done, right? It's sort of generational. I kind of want to get some lightning round questions in.
Okay, let's do it.
So I know you haven't mentioned it yet, but knowing that you do like to travel, where in the world would you go and why?
So, another thing that got interrupted by the pandemic was travel.
Yes.
And my husband, his family's from the Philippines, and that was one of the places that we had planned to go. in 2020, and we still haven't managed to come back around and plan that trip. So I'd really like to go to the Philippines and understand what his parents went through as young teenagers and, preteens during World War II, because his parents are a little bit older. I've never been able to actually go there, and my husband has never been either. So I think it's a really important thing for my children and for my husband to see. And, for me, I'm tickled to be able to understand a little bit more about his family and their history.
Wow, great. What would you consider the greatest scientific discovery of our time?
Ooh. I think penicillin was a real game changer.
Yeah.
And I think the first smallpox vaccine was also a game changer. So understanding that cowpox was very similar to smallpox and figuring out that if you immunize against cowpox, you prevent smallpox. So I think those are some cool things.
I always have a very consequential question as well. Greatest scientist, between Bill Nye or Mr. Wizard?
Can it be a real scientist?
Well, that makes it less funny than having to choose between Bill Nye and Mr. Wizard. But yes, you go ahead and tell me.
Bill Nye's a real scientist. Yeah. I think a scientist that I have always really looked up to is Linus Pauling. He actually won 2 Nobel Prizes unshared. One of them was for his research in understanding protein structure. And his other one was actually the Nobel Peace Prize, which he won for his efforts at, going against the nuclear escalation in the Cold War. So I think he is kind of my science idol because of that. 2 unshared Nobel Prizes, one of them a Peace Prize. I think that's really cool.
Well, that's actually better to know than my question anyway. Well, again, thank you so much for coming on the show today.
Thank you for having me. It's been a lot of fun.
Beyond J is a production of University Communications at Sacramento State. Our producer is Jonathan Morales. Photography and videography by Bibiana Ortiz. Additional research by Cynthia Hubert. And editing by me, your host, Philip Allstott. If you liked this episode, please leave us a review and consider following us on your favorite podcast platform. If you have questions or comments, email us at communications@csus.edu and visit us online at csus.edu/news/beyondj.